So we'll continue discussion on time-dependent perturbation theory. So today the topic is the transition probability for constant perturbation. So we already found out a detailed expression for transition probability in time-dependent perturbation theory. So in the first order approximation, what was the uh, expression for the transition probability? The transition probability we can represent by symbol PIF, which is modulus of minus I by h cross integral 0 to t e raised to I omega fi t prime, then inner product state psi f operator v is function of t prime state psi I dt prime mod square. Okay, so if you perform this, then we'll find what is the probability for transition from energy ei to energy ef. Okay, so this difference ef minus ei is denoted as h cross omega fi. So omega fi is a frequency corresponding to this transition. So whether it is probable or not probable, so all those things we can calculate by finding this expression. And recall this v is a perturbation. So what was the expression for the total Hamiltonian? The total Hamiltonian takes the form h0 plus v, which is a function of time. And this perturbation is non-zero for some small time interval, and it is zero otherwise. And the energy eigenstate corresponding to the Hamiltonian h0, the free part of the Hamiltonian, is expressed as the state psi, or in general state psi n. That is h0 acting on the state psi n is expressed as En psi n. So ket psi n is the energy eigenstate corresponding to H0 with the eigenvalue, energy eigenvalue En. Okay, so if you find this mod square, we'll get the total probability for this transition from the state psi I to the state psi f. So we can find the transition between any possible states by using this expression in the first order approximation. When you're going for higher order approximation, then there will be more complexity. Okay, so today's task is to find the expression for transition probability for a constant perturbation. So that means, suppose if v of t equal to v always. Okay, suppose if it is a constant, if it is not depending upon time, then for some time interval, so for 0 t up to tau, then what about the transition probability? Okay, so we can use this expression. Only thing is, instead of v, it's a function of t prime, I will just put the constant v there. So that is the only difference. So the probability from state psi I to f is modulus minus I by h cross integral 0 to t e raised to I omega fi t prime, the inner bracket psi f v psi I dt prime mod square. So since this v is not a function of time hereafter, so I can take this inner product outside this integration. So this would become minus I by h cross, the inner product psi f v psi I, then integral from 0 to t e raised to I omega fi t prime dt prime, and again the entire mod square. Okay, so this we can write as, so minus I mod square will be plus 1, so 1 by h bar square, then inner product psi f v psi I mod square. And if you integrate e raised to I omega f t prime, what you'll get is e raised to I omega f t prime divided by I omega phi, and the limit would be 0 to t. Okay, so this I can write. Okay, now there should be some mod square here. I forgot. So 1 by h bar square modulus of psi f v psi I mod square. If you put this limit, what you'll get is e raised to I omega fi t minus 1 all divided by I omega phi, the mod square. Okay, so what you want is we can take e raised to I omega phi t by 2 commonly outside. So this can be written as, better we copy this into the next page. Okay, so this is 1 by h cross square, the magnitude of psi f v psi I mod square, then e raised to I omega fi t by 2 times e raised to I omega fi t by 2 minus e raised to minus I omega fi t by 2 all divided by I times of omega phi, again all mod square. So this mod square, that would be equal to 1. So 1 by h bar square, the inner product psi f v psi I mod square. This would remain as 2 I sine omega fi t by 2 all divided by I omega fi, the mod square. So finally the result would be 4 by h bar square, the modulus of mod square of the inner product psi fv psi I, then sine square omega fi t by 2 divided by omega fi square. So this is an the square of sine function. So obviously this probability will vary with the time. So you can plot this probability of transition as a time graph. So how will it look like? So better you can have a graph. So the horizontal axis can be omega fi, and the vertical axis can be sine square omega fi t by 2 divided by omega fi. So this graph would be maximum, get maximum when omega fi tends to 0. So when omega fi tends to 0, you'll get maxima there. Then it would oscillate. Good. So when you get omega, when omega Fi is 2 pi by t, you'll get 0, and at 4 pi by t, you'll get 0, and here also my omega Fi is minus 2 pi by t, you'll get 0, and minus 4 pi by t, get 0, and so on. Okay, so it will have maximum at when omega Fi is 0, and the peak corresponding to t square by 4. Okay, so when t tends to infinity, what would happen is this width of this graph will reduce and the peak will increase. Okay, so this peak, the height of the peak depending upon t square, and the width of the peak is depending upon inversely proportional to t. So when t tends to infinity, the peak will be very high and sharp, so that means the function would become a Dirac delta function. So when t tends to infinity, this PIF will take the form of Dirac delta function. So we already have a functional form of Dirac delta in this way. It is when limit t tends to infinity, sine square xt divided by pi x square t is a Dirac delta function, delta of x. So what is our the transition probability? So PIF, so that we have already seen in the uh, last page, is 4 by h cross square inner product psi f v psi I all square, then sine square omega fi t by 2 divided by omega fi square. So when t tends to infinity, what would be the form? So this PIF, the probability of transition, will take the form. So this you can do it yourself. So I am just writing it here. It will be 2 pi times t by h cross the mod of or mod square of the inner product psi fv psi I, then the Dirac delta function ef minus ai. Okay, so remember this Dirac delta function ef minus ei, where ef minus ei is nothing but h cross omega fi. Omega fi is the transition frequency. Okay, so if you look at this, the probability of transition increases when as t increases. Okay, so here better we can define the transition rate. And transition rate is the probability divided by the time. So transition rate is usually denoted by symbol gamma. So transition rate from I to F. So I have to divide this with t, and you will get the expression 2 pi by h cross inner product psi f v psi I mod square the Dirac delta function ef minus ei. Okay, it's good. So this is the transition rate. The transition rate, if you look at this expression, the transition rate is a constant if the perturbation is constant. Okay, so that is the result that we are getting, and this Dirac delta function guarantees that the conservation of energy. It is the transition rate would be non-zero only when EF is equal to EI. Okay, so you can recall the Dirac delta function. Any Dirac delta function would be non-zero, or it would be zero when x not equal to 0. So if the argument is 0, then only this function has some value. So therefore, the transition rate will have non-zero value only when f equal to I. So it actually helps us, or it guarantees that the conservation is happens here. Okay, so there is no violation of conservation of energy in case of the constant perturbation. So that is what we are getting here. Okay, now from this we can have another result which is known as the Fermi's golden rule. So that will also I will mention. So Fermi's golden rule. Okay, suppose you have a continuum of energy levels, so very large number of energy levels here, and then if you have a continuum of energy level, it is customary to define the density of state. So usually denoted by symbol rho e. So rho e times dE, it is a number of states between E and E plus dE. So if we have some energy E here, and you have some other energy E plus dE. So how many states are available between these two energy levels, that you can find by denoting, or that you can denote by the symbol rho of E dE. So this rho of E is called density of states. Okay, so if your the final energy as a continuum of states, then you can find the transition probability by integrating the transition rate. Okay, so if that is the case, how could you find the total transition rate? So total transition rate by symbol WIF, and which is integral gamma IF. The total transition rate WIF equal integral gamma IF rho of EF df. So gamma if is the transition rate from the state I to f. So if as f is continuum, then we have to find the transition rate for each final energy state. Okay, suppose is ef, 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 and is ei. And if you want to know what is if you want to know the total transition rate, first you should know what's the transition rate from ei to ef, then ei to some higher energy level, then ei to some other energy level, and so on. So if you add all those transition rate, we'll get the total transition rate. Okay, now what is gam for constant perturbation? What is gamma if? Gamma if is 2 pi by h cross mod of psi f v psi I mod square f minus e. Okay, so if you integrate this gamma if over the uh, final energy levels, then would be integral. So in this integration, I can put this 2 pi by h cross as constant, and the inner product psi f v psi I square, that is also a constant. So the integration is only here. So the direct function ef minus a, because the integration variable is only ef, and rho ef into dei. Okay, sorry, def. Now this result of this integration is very trivial to us, because the by the definition of Dirac delta function, I can say that if you integrate over EF energy variable, then I have to just replace all EF with EI in the function. So this become the result of this integration becomes simply rho at EI. So this become 2 pi by h cross the inner product psi f b psi I mod square, so rho at EI. So that is your WIF. So this is a remarkable result, and this result is called the Fermi's golden rule. So that is for constant perturbation. If we wait for a long time, the transition rate would be a constant. Okay, so we have to think all this result that we are getting for t tends to infinity. Okay, so this gamma if we are getting when t tends to infinity. So when t tends to infinity, the probability of transition take this expression, and the transition rate take this expression. So if you uh, wait for long enough time, then the transition rate is constant for constant perturbation. And it is proportional to density of states of initial state. Okay, so the transition probability is not depending upon the density of states of a finite energy level. It depends upon density of states of initial energy level. Okay, so this complete thing is called the Fermi's golden rule. So if you wait for a long time, okay, if you wait for long enough time when t tends to infinity, the transition rate is a constant for constant perturbation. It is proportional to density of states of initial state. Okay, so with this we can stop today's discussion. So what we have found is we have just found the transition probability for constant perturbation. So if v is constant in time for some time interval, then I can find the transition probability takes the form of this, the 4 by h square square, and it is varying with time. Okay, but even though it is varying with time, it has very peak value when omega fi tends to 0. Okay, so when omega phi is 0, it has the maximum value. At all other omega phi's, the transition probability is very small. Okay, so now if when t is very large, what happens is this peak will become very narrow, and it will become very high, very tall. So that corresponding to Dirac delta function. So when t tends to infinity, the probability of transition will take the form of Dirac delta functions, and this is the form. Okay, so and it is proportional to t. Transition probability would be proportional to t, and the transition rate is independent on t. The transition rate takes this form. Okay, and again, so in both the probability of transition and as well as transition rate, it depends depending upon the Dirac delta function ef minus ei. So that means it has non-zero value only when if ef equal to ei, that is when the final energy level is same as a initial energy level. Otherwise the transition probability will be 0 when t tends to infinity. Okay, so thereafter we discussed about the Fermi's golden rule. So if you have a continuum of state, okay, if you have the continuous energy levels, then we can define what is called the density of states, rho of E, and its definition we have discussed. Rho of E into D is the number of states between the energy level E and E plus D. If that is the case, if you have a continuum energy levels, then the total transition rate would be the integral of gamma IF over the final energy states. Okay, so rho of EF DF would give the number of the final energy states. So I have to just add all the transition rate in order to get the total transition rate. Now, if you integrate this, it will get very simple expression. The total transition rate will become 2 pi by h cross the mod square of inner bracket psi of p psi I, then rho at EI. Okay, so which means the total transition rate would be a constant if you have a constant perturbation and if you're waiting for a very long time, and moreover it depends only on the density of states of initial energy level. Okay, so with that we'll stop here. So in the next class we'll discuss about what would be the transition probability if we have a harmonic perturbation. Now strictly speaking, the constant perturbation will not come under the purview of time dependent perturbation theory, but it is okay uh, because what we have done is we are not discussing v of t is constant throughout. The v of t is constant for a small time interval. So in that sense this problem comes under the problem of time dependent perturbation theory. Otherwise we cannot deal it, because that become time independent perturbation theory. If v is constant throughout all the time, then it is not correct. But here what we have discussed is the v is constant for small amount of time. Okay, this v of t which is constant v of t equal to v for small amount of time, and it is zero otherwise. So that is why we have discussed this problem as a time dependent perturbation theory problem. Now here we in the next section we'll add a one more term, that is we'll add a harmonic perturbation term to discuss further. Okay, so we'll see in the next class. Thank you.